Calc 3, Chapter 11. This is the first section. And we're going to be, for the next few sections, we're going to be studying vectors. And what I'm going to do is I'm not going to assume any background knowledge in vectors. This could be good or bad, I mean, depending on how much experience that you've had dealing with vectors. But nonetheless, hopefully, even if you have had, say, me for linear algebra, or you have had vectors in your physics courses, hopefully this will serve as, at a minimum, a refresher, and maybe you'll pick up on some more of the theory, more of the why in some of this in this topic. So let me begin this way. So look, there's certain quantities out there that you can capture all of the relevant information of that quantity by simply giving a single number, which we will call the magnitude. In other words, if you can, for example, temperature, you can capture all of the relevant information about temperature by just telling me it's 80 degrees outside. So you don't have to give me any more information. Of course, it'd be nice if you told me which, it told me if you're using Fahrenheit or Celsius or etc. But nevertheless, mass or temperature or area or volume, all of the information can be captured in a single number. Now, there are other quantities out there that is not true for. For example, if you were to tell me, for example, well, let's just take force. If you were to tell me the force at which you are applying pressure, or a force at which you are pushing on an object, that doesn't give me enough information, right? So let's assume this is some object. Don't get jealous about my ability to draw throughout this class. Okay, just contain yourself. But if you told me that you were applying a force, right? You were pushing on this object. It just simply telling me the magnitude of the force is not enough information, right? Because how do I know? Are you applying the force with the horizon? Are you applying the force in this direction or this direction or this? Right. This is the angle at which you apply the force is going to matter if we're talking about how that force is going to affect the object. Now, this is also true for things like velocity, right? If you were to look at your, if you were driving, if you were to look at your speedometer would tell you, say you're going 55 miles per hour, right? Now that is the speed at which you are traveling, but that's not a velocity, because a velocity, you would also have to tell me at which direction you are going that speed. So nevertheless, vectors, what we're going to be discussing here, vectors are those quantities that require more than just a single number, right? Vectors require both the magnitude as well as the direction. Now, if you kind of follow me up here to figure 11.1, we're gonna start off discussing vectors, just a geometric interpretation, right? Where we don't need to be with any type of bounded by any type of coordinate system. We are just going to discuss some of the geometric properties of vectors. So notice the way we're going to think about vectors. So we can think about some starting point, right? Some initial point. We'll call that point P. And now, from point P, we're going to travel in a certain direction. And we're going to travel all the way until we reach another point, which we're going to call Q, right? So we are traveling from initial point to terminal point. Now we refer to this, right? This is not just a segment, right? Because a segment, it's not just simply a segment, because a segment might have the same magnitude as this segment that we're looking at, but the direction is important, right? We are not traveling from Q to P. We're traveling from P to Q. So we want to indicate that with some type of arrow. And now what we have is what we call a directed line segment. All right. So the shorthand that we use for directed line segments looks something like this. So this is simply telling us from P to Q. So now, what is the difference between a directed line segment and a vector? Well, what's important to know is, and if you don't mind, you'll kind of follow me down here. I'll do my best using a stylus to bounce back and forth as to where my eyes are, but I'm going to be looking at figure 11.2 along with this statement of equality. Now, so the question I had stated was, what is the difference between a directed line segment, right, this segment heading from P to Q, or something we might call vector V? Well, to answer that question, we need to discuss when would we consider vectors to be equal, right? Equivalent. What criteria would need to be established in order to make a statement of equality regarding two vectors? So let's see if you can follow me here. So let's assume that we have some vector v, we have some vector u, and notice that in order for let me see if I can phrase it this way. This might be simpler. So the criteria that needs to be met in order to say you have equivalent vectors is that they must have the same length, and they must have the same direction. So if you follow me here to figure 11.2, notice that each of these vectors drawn here, although they are positioned in this plane in different positions, each of them has the same length and the same direction. And that is the criteria that we need to be able to say that each of these vectors, these directed line segments, each of these are equal to each other. So now, let me get back to my original question. So how do we think about directed line segments versus how do we think about vectors? So here's the simplest I can make it. So when you have a directed line segment, P to Q, if you were to think about all the possible variations here of P to Q, right? So for example, you could have P to Q here in your plane, or you could have it here, or you could have it here. When you start to think about, if you were to try to capture the set of all of these variations, that set would be what we mean when we say vector V. I'll say that one more time just to make sure you understand that. I hope it makes sense that the class of all the directed line segments, right? All of these, the class of all the directed line segments that are equal is what we call the vector. Okay. So a vector is just a set. It's the set of all the various directed line segments that meet these conditions. All right. So let me see if we can let me see if I can jump in and we can get started here. So example 1. What we'd like to do is we'd say we're making a statement. Let V be represented by the direct line segment from 0, 0 to 3, 2, comma. All right, now, so if you've always struggled with word problems, let me see if I can help. So just like in conversation, we have pauses, right? We have periods when we're writing. We have commas. And basically those pauses are there so that the listener or the reader, and if we're dealing with commas, can to make sure that they grasp what was said prior. So you don't, in my opinion, this is just my opinion, there's no point reading math questions like you would read a novel. Read until you get to some type of break, some type of comma or period, and pause, and don't move any farther until you fully understand what comes prior to that comma. So again, we're basically saying let V be represented, and I'm going to see if I can capture this information. We're saying let vector V. Now, in your textbooks, it's often common to use a bold when you're writing a vector. I will instead use a little arrow over the letter so that it can be seen clearer. But nevertheless, we're basically saying let V be represented by the directed line segment from 0, 0 to 3, 2. Now, we can think about the initial point, since we're moving from the origin, from 0, 0 to the terminal point, which we can just label as Q. All right, so this is how we can make the statement that V is simply equal to this directed line segment, P to Q. I'm going to do the same thing with U. Let me get back up here and read. It says, and let U be represented by the directed line segment. Now we're going from 1, 2 to 4, 4. So now we're going from the point 1, 2, and we're proceeding to the point 4, 4. All right, now I will just use two other letters. So we'll just label the initial point for U, we'll label it R, we'll label the terminal point S. So the statement being made here is that U is represented by the directed line segment R to S. Interesting. Now, the goal is to show, let's see if I can move this without messing anything up. The goal is to show that vector V is equal to vector U. So do you recall from the previous page the two criteria that we must show? Right? To make a statement of equivalence, we must show what? Well, same magnitude, and we must show same direction. All right. So let's start with magnitude. So the good news is we have a formula, right? A distance formula that we can use to capture the distances between any 2 points within a plane, right? So that distance formula, if you recall, is just the square root of y sub 2 minus y sub 1 squared plus x sub 2 minus x sub 1 squared. So the goal right now is to find the distance from P to Q and the distance from R to S. Only I don't want to continue to use that language here, distance. I'm going to use the language of magnitude. So, and we're going to capture, I will give you the notation you're going to see me use in just a second. I will have on the next page as well. But let's start with the magnitude from P to Q. Right, so you see this double absolute value symbol is what we're going to use to represent magnitude. And we want the magnitude from R to S. All right, so I'm going to go through this quickly. We'll start with P to Q. So at this stage, we just need to label, we can label this x sub 1. I'm going to write with my stylus, but it's going to be erased when I move my stylus. We can label this x sub 1, x sub 2, my apologies, let me try that again. X sub 1, y sub 1, x sub 2, y sub 2. Right, so once we have them labeled, we can then just simply plug each into the distance formula. So let's try to move quickly through this. So that gives us the square root of 3, right? So y sub 2 is 3 minus 0 squared plus 2 minus 0 squared, right? Which is simply the square root of 13. Let's do the same thing. Now we're moving from R to S. All right, again, going through labeling, you can, x sub 1, y sub 1, x sub 2, y sub 2, and plugging in. So I have 4 minus, let's see here. Yeah, I got 4 minus 2 squared plus 4 minus 1. Squared. And again, if you work out that arithmetic, you get the square root of 13. So far so good. We can state that the first criteria has been met. It's the same magnitude. Now, how do we talk about, or how would we find the direction, right? How do we find the direction P to Q or the direction R to S? Well, the good news is when we're dealing with lines in a plane, right? When we're dealing with vectors in a plane, we can think about direction as slope. But I don't want you to lean on this too much, because once we move outside of a two-dimensional axis and we move into a three-dimensional axis, slope no longer carries the meaning that it did in a two-dimensional axis, right? So really, later we'll refine this method and we'll start to talk about the angle, because the angle is something that can carry forward into higher dimensions. Slope is something that we know, so we'll just use the tool as it for right now. But all we're simply stating is we want the slope, right? We want the slope of P to Q, and we want the slope of R to S. And you know how this works. If you give me 2 points, I can find you a slope. That's easy enough. So we're going to get 2 minus 0 over 3 minus 0. And we're going to get 4 minus 2 over 4 minus 1. So we end up with a slope of 2/3 for the vector v, and we end up with the slope of 2/3 for the vector u. So we have met both criteria, and now we do get to make the statement that vector v is equal to vector u. Okay, so we're gonna, a little bit of vocabulary that we're gonna, I want to make sure we have a good, strong command of before we move any farther. And the first bit of vocabulary I want to make sure you understand is the idea of what we call standard position, right? The standard position of a vector. And so, as you recall, right, take a look at figure 11.4. So here is vector, we got vector v, which is the directed line segment from P to Q. Now, we've already established that there's a whole lot of vectors, right? There's an infinite number of vectors that might meet this criteria, being the same magnitude, same direction. But what we like to do when possible is we like to position the vector, right? In other words, we could have the vector up here, but we would drag and drop this vector such that the initial point is going to start at the origin 0, 0. And we do this because it just simplifies things. For example, it simplifies using the distance formula greatly. You'll see that in just a second. But all you need to know as of right now is that standard position of a vector just simply means the initial point is at the origin. Okay? Now, it doesn't tell us any other information. It just simply tells us that the initial point is at the origin. So we'll come back to that in just a second. So one of the things about once you place a vector in standard position, right? So if I had my vector here and I were to drag and drop that vector to here, so it's in standard position. Once the vector is in standard position, we can represent that vector. We can represent vectors a few different ways. If you've had any exposure to physics, you may have seen the IJ notation when discussing vectors. But another way to represent a vector is what we call the component form. Okay, but to represent a vector in component form, you must have the vector in standard position. I'll say that one more time. So if you see a vector in standard position, you know that you, let me phrase it differently. If you have it, if you're given a vector in component form, you know that it's in standard position. Okay? So now let's see if we can talk a little bit about what do we mean by component form. So let's start with the idea that you're going to have to kind of follow me up here. So notice that initial point P, it's in component form, so we know that's at the origin, 0, 0. And notice the notation that they're using for the terminal point. I'm going to write that just slightly larger. So they're basically saying vector V, that this initial, or this terminal point, they're using, instead of using X and Y, they're using V with subscripts, right? So they're saying, I'm trying my best to capture this in the space that I have, but instead of using X, Y, they're letting V sub 1 represent X, and they're letting V sub 2 represent Y. All right. Now, the notation that we use for component form is going to look like this. All right. And we're going to have a comma here to represent each to distinguish each component. Now, the good news about it being in standard form is that you can now capture the information of the vector by simply giving the terminal point. And I'll say that again. Once you have your vector in standard position, where the initial is at the origin, you can capture the information of that vector by just giving the terminal. So this is what it ends up looking like. V sub 1, V sub 2. That's all we need to represent vector V. All right, so let's discuss a little bit, just for a second, about how you would convert, convert from a vector. Say if you did have a vector out like this, how would you convert it to a standard position? And that also allows us to, I'm going to of how to write it in component form. So basically, I'm answering two questions at the same time. How do you get a vector geometrically into standard position, and how do we get a vector into component form? So let me see if I can grab all that information from the space that I have. So the way I'll do this is, let's say point P is located at x sub 1, y sub 1, and point Q is at x sub 2, y sub 2. All right? And now we want to, so geometrically, if I hope you're not daydreaming on me, but come back to me. Again, geometrically, how do I drag and drop this vector so that it's in standard position? Well, the way you do that is it's very simple. You're just going to subtract component by component. So we're going to take x sub 2 minus x sub 1, comma, y sub 2 minus y sub 1. Let me rewrite that. Y sub 1. All right, you with me? So if I knew these points, right, 2, 2, 4, 4. If I knew these points, then taking the terminal point, right, x sub 2 minus x sub 1, y sub 2 minus y sub 1, this would get me into component form of vector V. All right, I hope that makes sense. This is how you get to here. All right, so let's discuss magnitude. So I told you that the notation that I would be using for magnitude of a vector looks like the following. So you have this, that's a double absolute value bar. But if you follow me up here to, normally the magnitude is just simply, now we're dealing in a plane here, the magnitude is normally thought of as by using the distance formula, except that can you imagine for just a second, can you imagine that I'm going to circle, if you have it in, if you have your vector in standard position, stay with me, don't come back to me, ready? If you have your vector in standard position, do you agree with me then your initial is at the origin, right? That would mean that this point and this point is at the origin, right? X sub 1, y sub 1 is at the origin. So that would mean you would be subtracting 0, minus 0. If this is 0 and this is 0, you can see how this simplifies your magnitude equation. And such, so now all we need for magnitude, once it's in component form, is just v sub 1 squared plus v sub 2 squared. Okay? All you need is this information squared plus this information, the square root of, I should say, and this information squared. All right, let's keep going here. So almost done with these definitions. So let's talk about, since we're talking about magnitude, we can think about it as the length, if you'd like. If you have a magnitude of 0 or a magnitude of 1. So this is what we would call a 0 vector. All right, so the way different books do this differently. The way I will normally make sure I'm writing the 0 vectors, I will write 0, but I'll still use the arrow over top of it so that you know that I'm discussing the 0 vector. And the 0 vector just simply means that the initial point and the terminal point share the same, or reside at the same location, right? Now, a unit vector simply has a magnitude of 1. All right, so got the theory out of or at least the definition part out of the way. Let's keep going here. So let's put this to use, right? Example 2. We're asked to find the component form, all right, and the length of a vector v. All right, so we want two things. We want the component form of v, and we want the magnitude, the length of v. Now, here's what they tell us. It has an initial point at 3, -7, right? So that's here. And a terminal at -2, 5. So let's put this to use. So I'm going to label that initial, we'll label that point P. All right, so that's at 3, -7. And that terminal, we'll just label that Q, is -2, +5. All right. And let's do this. So we want to get from, to the component form. All right, so component form. So we're told that P to Q is equal to V, but we just want the component form of V. All right, here we go. So all that's required here is that you just, you can go through and label this x sub 1, y sub 1, x sub 2, y sub 2, if that's helpful. And then let's just fill everything in. So we got, all right, so -2, and that's x sub 2 minus x sub 1, so -3, right? X sub 2 minus x sub 1, y sub 2 minus y sub 1, and now we have 5 y sub 2 minus what? Minus -7. All right. So the result is the following. So -2 minus 3, so -5, and we got +7, so that's 12. So there you go. There's the component form of V. So if you wanted to draw this, but you wanted the initial to be at the origin, then here you go. All right, and now that we have it in component form, let's go ahead and find the magnitude of V. And what we saw from the previous page is just going to be the square root of v sub 1 squared plus v sub 2 squared. So this is our v sub 1, this is our v sub 2, and this is just some simple arithmetic from here. So we got the square root of negative 5 squared plus 12 squared. There you go. Okay. So the way it works in mathematics, right? If you can have this idea, right? This idea of vectors, but to a mathematician, the first thing that a mathematician is going to want to know is, okay, if I accept your idea, right, your new idea that you're calling vectors, the mathematician is going to want to know, well, what operations are allowed, right? How do I combine vectors? How would I add them? How would I multiply them? Subtract them, scale them, etc. So the operations, the vector operations, we're going to go through very quickly. Notice that the way I realize that you can read this, right? But I'm just going to go as quickly as I can so that you understand with a stylus, but just so that you can hear it from me. So they're saying, all right, you have a vector u and you have a vector v. What if you wanted to combine the two vectors? What would that look like, right? So the sum, the vector sum. So how would you add u and v? Well, simple enough. To add u and v, you would take the x component, the horizontal component of u and v. You would combine those, right? So notice it's u sub 1 plus v sub 1. And you would also combine the vertical component of u and v. So u sub 2, v sub 2. What I will state, and this is the result of this, is a new vector. Now sometimes they'll give this a new notation, right? But I want you to understand this new vector, the notation is this until told otherwise, right? If you add u and v, this is your notation. This is a whole new vector. Just normally they will say that, they'll make up something else. They'll say, let that be represented by, say, r. Okay, so we're going to allow c to be, so c is a scalar, right? So this is going to be just a magnitude, right? Just it can be a positive, a number, negative number, it can be 0. A scalar of 0 doesn't, well, I won't go into that really quickly, but the way you would think about it is if you wanted to scale a vector, right? So if you take a look down here, so if this is your vector v. Now you could double v, right? Double the length. You could cut the length in half, right? So this would be half of v. Now notice that the scalar is a half. This would be double v. Notice that the scalar is 2. But the simple enough is if you want to scale a vector, you're just simply going to scale each component, right? So you scale the x, the x portion, the y portion, the horizontal portion, the vertical portion. How would you interpret the negation, right? The negative of v. So again, the way you got to think about it, if this is v, what would negative v look like, right? Well, the negative, in this case negative 1, just changes the direction at which the vector is going. It doesn't change the magnitude, right? To multiply by 1 you're going to preserve the same magnitude, but you are going to change the direction. So that's negative v. last, this is probably important enough to write, or at least place to memory. You're probably best to think about when you're subtracting vectors, right? U minus v. You're probably best to think about that instead as u plus the negative v. So that would be a better way of thinking about the difference. All right. Again, we're going to move through this quickly. We're going to take a break here in just a second, but an interesting, you don't have to write any notes here, okay, but just an interesting geometric interpretation of u plus v, right? So here's vector u, here's vector v. So to ask the question, what is u plus v? Geometrically, right? Geometrically, we don't need to know u and v. We can find this sum geometrically. And notice what we're going to do is we're going to take v and we're going to move it so that the initial of v, right? So here's v. Notice that the initial of v is aligned with the terminal of u. And here's what's extremely interesting. This diagonal that's created from this parallelogram, this diagonal is u plus v. Right? So notice that you don't need to add anything. You could find the sum geometrically. I would encourage you in your own time. You can look through, visually how to think about the geometry of, just like we did above with addition, how to think about scalar multiplication, how to think about subtraction. For my engineers, for my scientists, a lot of times we gloss over things like this, and we're really good at, say, the recipes, right? Getting to the answer in that fashion. But here's something that you should take away. You'll know you're really getting good at mathematics. Okay, here's how you'll know. You'll know that you'll start to be able to anticipate if I just change the geometry. You would anticipate how that's going to change the algebra, and then you can anticipate if I change something in the algebra, how that's going to affect the geometry. And for someone like me who's very visual, I need to see the geometry if you want me to understand these things. The last bit of information before we take a break is, especially in physics and engineering, what we call the sum of two vectors is the resultant vector, right? So this u plus v would be the resultant vector. It's the result of adding u and v. All right, we'll go ahead and call it quits, and we'll come back for the remainder of this section in the next video. See you then.